So here's the puzzle. If it's just a distance, why does it feel unreachable? Why, when we hear that the nearest star is about 4 light years away, do we quietly translate that into, that's beyond us? Why, when we hear that the nearest star is about 4 light years away, do we quietly translate that into, that's beyond us? We've crossed oceans. We've flown around the Earth. We've landed on the moon. We've sent spacecraft past Pluto. We are a species that moves. We build engines precisely because we don't like limits. So what's different about a light year? At first glance, the answer seems obvious. It's too far. Our rockets are slow. Even our fastest spacecraft would take tens of thousands of years to travel that distance. But suppose I hand you a better engine, not a chemical rocket, not nuclear fission, something far more powerful. Suppose I say, accelerate as hard as you like, keep pushing. Would you eventually reach light speed? Would you eventually cover a light year in less than a year? Here's where the universe quietly says no. Not because of engineering, because of geometry. To understand that, we have to start with something very ordinary. Imagine you're riding in a car moving at 60 kilometers per hour. You throw a ball forward at 20 kilometers per hour relative to the car. Someone standing on the roadside sees the ball moving at 80 kilometers per hour. Speeds add. That's so familiar we don't even notice it. It's embedded in how we think. Motion stacks. If I run forward on a moving walkway, I go faster relative to the ground. Now imagine you're on a smooth train moving at constant speed. Inside, you toss a ball straight up. It rises and falls straight back into your hand. You could perform that experiment all day and never detect that the train is moving. Galileo understood this deeply. He argued that if you're inside a smoothly moving ship with no windows, the laws of physics look exactly the same as if the ship were at rest. There is no absolute rest. Motion is relative. That principle survived for centuries. Newton built mechanics on it, and for everything involving slow speeds, meaning speeds much smaller than the speed of light, it works beautifully. Now replace the ball with a beam of light. You're on the train again. You turn on a flashlight pointing forward. Inside the train, you measure the light moving away from you at the speed of light, about 300,000 kilometers per second. Someone standing on the ground sees the train moving at 60 kilometers per hour. So what speed do they measure for the light? Common sense whispers they should measure light speed plus 60 kilometers per hour. That's what happens with balls. But experiment says otherwise. No matter how fast the train moves, the person on the ground measures the same speed of light. Exactly the same. Not approximately, not close enough, the same. This is not speculation. In 1887, Albert Michelson and Edward Morley performed an exquisitely precise experiment to detect Earth's motion through what physicists believed was a medium called the ether, the substance through which light waves were thought to travel. If Earth were moving through this ether, the speed of light should vary slightly depending on direction. They rotated their apparatus, expecting a tiny shift in interference fringes. They saw nothing. The speed of light was constant. This was a crisis. Physicists tried to patch the theory. Maybe objects contract in the direction of motion. Maybe time changes slightly. These were clever but artificial fixes. Then, in 1905, Einstein asked a bold question. What if the constancy of light speed is not a problem to solve, but a principle to accept? What if two statements are both true? First, the laws of physics are identical in all inertial frames, Galileo's principle. Second, the speed of light in vacuum is the same for all observers regardless of their motion. If you hold both of those, something has to give. And what gives is not light, it's space and time. Let's make this concrete. Imagine a clock built from two mirrors facing each other, with a pulse of light bouncing between them. Each round trip is one tick. If the clock is sitting next to you, the light travels straight up and down. Now imagine the clock moves sideways past you at high speed. From your perspective, the light follows a diagonal path, up and over, down and over, because the mirrors move sideways while the light travels. The diagonal path is longer than the straight path, but the speed of light must remain the same. If the path is longer and the speed is unchanged, the time per tick must increase. The moving clock runs slow. This is time dilation, and it's not philosophical. Fast-moving particles called muons, created high in Earth's atmosphere, live longer than they would at rest. They reach the ground precisely because time slows down for them. Atomic clocks flown on airplanes show measurable differences. GPS satellites must correct for relativistic effects, or navigation errors would accumulate rapidly. Time is not absolute. Now let's turn to length. Suppose a spaceship rushes past you at high speed. To measure its length, you must record the positions of its nose and tail at the same time. But simultaneity is relative. Two events that are simultaneous in your frame are not necessarily simultaneous in the ship's frame. Because of this, the moving ship's length in the direction of motion is shorter than its rest length. Length contraction. So as speed increases, time dilates and length contracts. Already we've shattered common sense, but we haven't yet addressed the energy required to reach high speeds. In Newtonian mechanics, kinetic energy increases as 1/2 mv squared. If you apply a constant force, velocity increases steadily. There's no upper limit. But relativity modifies the relationship between momentum and velocity. Relativistic momentum is not simply mv. It includes a factor that grows dramatically as velocity approaches light speed. This factor, often called gamma, is 1 divided by the square root of 1 minus v squared over c squared. As v approaches c, the denominator shrinks towards 0. Gamma grows without bound. Momentum and energy both scale with gamma. That means each additional increment of speed requires more energy than the last. The closer you get to light speed, the steeper the energy curve becomes. Graph it in your mind. At low speeds, the curve looks like Newton's familiar gentle rise. But as v approaches c, the curve shoots upward toward infinity. To reach exactly c would require infinite energy. Not a lot, infinite. And infinite energy is not an engineering problem. It is physically impossible. So no object with mass can reach light speed. But what about getting close? Suppose you accelerate to 99% of light speed. That's extraordinarily fast. At that speed, gamma is about 7, so your kinetic energy is roughly 7 times your rest energy minus 1 unit of rest energy. That's already enormous. Now go to 99.9% of light speed. Gamma jumps to about 22. Go to 99.999%. Gamma becomes about 224. Each additional decimal place costs staggering amounts of energy. Particle accelerators demonstrate this beautifully. At facilities like CERN, protons are pushed to 99.99999% of light speed. Engineers pour in colossal energy for tiny increases in speed. The particles never cross the barrier. Nature enforces the rule. Now here's where it gets fascinating. From Earth's perspective, if you travel at 99.9% of light speed, it takes just over a year to travel 1 light year. But from the traveler's perspective, because of length contraction, the distance to the destination shrinks. At 99.9% of light speed, the gamma factor of about 22 means that a 1 light-year distance contracts to roughly 1/22nd of a light-year in the traveler's frame. You could cross it in a matter of weeks of your own time. Relativity allows the traveler to experience a short journey, but Earth observers would see more than a year pass. No one sees faster than light motion. The limit remains intact. Now let's deepen this with the twin paradox. Imagine twins. One stays on Earth, the other accelerates to near light speed, travels to a distant star 4 light years away, turns around and returns. From Earth's frame, the journey might take a little over 8 years. But because of time dilation, the traveling twin ages less. When they reunite, one is younger. This is not a paradox once you include acceleration. The traveling twin changes frames. The Earth twin does not. Their paths through spacetime are different lengths. And here we arrive at a powerful geometric insight. In relativity, time is like a distance in spacetime. Each object traces a path, called a world line. The amount of time experienced by an object is proportional to the length of its world line. For objects moving inertially, the straight world line maximizes proper time between 2 events. Acceleration tilts the path in spacetime and reduces the experience time. If that sounds abstract, imagine space-time diagrams. Draw time upward and space horizontally. Light rays travel at 45-degree angles. That 45-degree line defines the boundary of possible influence, the light cone. Anything inside the cone can be causally connected. Anything outside cannot. Massive objects must travel inside the cone. Light travels exactly along its edge. To exceed light speed would mean stepping outside the cone, into a region where cause and effect reverse in some frames. The light cone is not just a diagram, it is the structure of causality. Now let's ask something deeper. Why does space-time have this structure at all? In the 1860s, James Clerk Maxwell unified electricity and magnetism. His equations predicted electromagnetic waves traveling at a speed determined by the electric permittivity and magnetic permeability of free space. That speed matched the measured speed of light. Light wasn't special because it was light. It was special because it revealed a property of space-time itself. Einstein realized that the constancy is not merely the speed of electromagnetic waves. It is the conversion factor between space and time. If you measure space in meters and time in seconds, c translates between them. It appears in every relativistic equation because space and time are woven together. Think of space-time as a fabric with a specific geometry, not Euclidean, but Minkowskian. In Euclidean geometry, the shortest path between 2 points is a straight line. In spacetime, the path that maximizes proper time is straight. Light's path is special. It has zero proper time. Photons do not experience time passing. From their perspective, though that word must be used carefully, emission and absorption are adjacent. That's extraordinary. Now consider acceleration. Suppose you accelerate at 1 Earth gravity continuously. For the first year, you feel normal gravity under your feet. Your ship's speed relative to Earth increases steadily, approaching light speed asymptotically. After a year of your proper time, you might be traveling at about 77% of light speed. After 2 years, faster still. If you flip around and decelerate symmetrically, you could reach stars dozens of light years away within a human lifetime of onboard time. But from Earth's perspective, much more time passes. Interstellar travel is not forbidden, but the energy requirements are enormous. To accelerate a modest mass spacecraft to relativistic speeds requires energy comparable to planetary scales. And even then, the light cone structure remains. You never exceed c. Let's push one more thought experiment. Imagine you could send a signal faster than light. Suppose you transmit a message instantly across a light year. In some reference frames, because simultaneity is relative, the message would be received before it was sent. With clever arrangement, you could construct a loop that sends information into your own past. Causality would collapse. Relativity's speed limit is not arbitrary. It protects logical consistency. So when we ask why we can't reach a light year quickly, we're really asking why we can't outrun causality, because a light year is defined using c, the maximum speed of influence. To traverse that distance in less than a year of Earth time would require faster-than-light motion, and that would require tearing the light cone. Nature does not permit it. Now, there are speculative ideas, wormholes, warp drives, solutions to Einstein's field equations that mathematically allow shortcuts in space-time. But they require exotic matter with negative energy density in macroscopic amounts, something we have no evidence can exist stably. So far, every experiment confirms the local speed limit. Cosmic rays, particle accelerators, astronomical observations all agree. The speed of light is invariant, and that invariance is not a nuisance. It is a window into the deep structure of reality. When we first measured it, we thought it was a property of light. Now we understand it is a property of space-time. The impossibility of reaching light speed is not a failure of ambition. It is a reflection of geometry. And here is the philosophical twist. Limits are often seen as restrictions, but in physics, limits often reveal structure. The impossibility of perpetual motion revealed conservation of energy. The impossibility of absolute simultaneity revealed spacetime. The impossibility of exceeding light speed reveals the causal architecture of the universe. When you hear that a star is 4 light-years away, you are hearing more than a distance. You are hearing a statement about how spacetime is stitched together. We cannot casually hop across that gulf because doing so would require violating the very geometry that makes the universe intelligible. Yet within that geometry, astonishing possibilities remain. Time dilation means that explorers could, in principle, cross vast cosmic distances within their lifetimes. Mass energy equivalence means a tiny amount of matter contains enormous energy, because c squared is enormous. The same constant that limits speed amplifies energy. It binds together electricity, magnetism, energy, momentum, space, and time into a coherent whole. We began with a simple question. Why can't we reach a light year? The naive answer was, because it's far. The deeper answer is, because space-time has structure. Because c is not just a number but a geometric boundary. Because cause and effect must remain ordered. And because energy grows without bound as we approach that boundary. In the end, perhaps the most remarkable thing is not that we are limited, it is that we can understand the limit. From a puzzling null experiment in the 19th century, through careful reasoning and bold conceptual leaps, we uncovered a new geometry of reality. We discovered that space and time are not separate stages on which events unfold. They are actors in the play. The light year is not a wall in space. It is a measure drawn from the deepest symmetry of the cosmos. We may not yet sail between stars with ease, but we have already traveled far. from bicycles and thrown balls to light cones and world lines. And in that journey of understanding, we have crossed a conceptual distance far greater than any light year. Because to comprehend the structure of space-time is to glimpse the architecture of reality itself. And that perhaps is the most extraordinary voyage of all.